Okay, so good morning, everyone. First of all, I would like to thank the organizer for having me today. And it's a pity I'm not in person. I would like to be there in person, of course. So for the people that don't know me, I'm Celeste Artale. I'm currently a postdoctoral fellow at the University of Padova, but also I'm a research visitor at Purdue University, so I am currently in the US. And so today I would like to talk about the host galaxies of binary compact object mergers across cosmic time. And these are my collaborators in this field in the studying the host galaxies of binary compact object mergers. So as an outline, I will just give a general overview about what are exactly the gravitational wave events I will referring to, and what are the detections and the current state of the art from LIGO-Virgo-KAGRA collaboration. Then I will focus on why we are interested in understanding more about the galaxy properties in the context of gravitational wave events. And I will mention some of the featured challenges, but there are so many that I will just mention a brief summary from my side. So I think more or less you know what are the gravitational wave events, are ripples in the curvature of space-time, and they are created by moving masses, while electromagnetic waves are created by moving charges. And as you know, gravity is the weakest of the four fundamental forces, and that's the reason the gravitational wave events are extremely small. And just about 7 years ago we were able for the first time to detect a direct gravitational wave event by LIGO detectors at that time. So, so this plot shows you the strain, on the y-axis. The strain is a way to quantify the amplitude of the gravitational waves as a function of the frequency of the wave. And this plot displays all the sources that we that can produce gravitational wave events that we can measure or detect. And in particular, you may hear, so the ground-based interferometers LIGO-Virgo and KAGRA can detect gravitational wave events from binary neutron stars, binary black holes, and black hole neutron star systems. But in the future, we expect to have, and in fact, there are forthcoming and some papers from other kind of sources that can produce gravitational wave events that we can detect in the future. So like, supermassive black holes, or for instance, LISA, or well, there are many more. But just to give you an idea, so in this case, for the ground-based interferometers, the strain is about 10 to the minus 20. And this means that these events distort the shape of the Earth by 10 to the minus 13 meters, which means about 1% of the size of an atom. So you can imagine this is extremely, extremely small, and it's amazing that we were able to detect such very small variation and this event. So nowadays, as I mentioned, we have two interferometers, LIGO in Livingston and Hanford in the US. We have Virgo in Italy, in Pisa, and recently the KAGRA interferometer, which is the first one that is underground, started to work. And the way we measure these distortions on the space-time is through these Michelson interferometers, and these tiny variations in the interferometry can tell us about different properties of these binary compact objects that merge, like for instance the masses of the two compact objects, the spins, the luminosity distance, and some other properties, and so among others. Now, just to give you an idea about how fast this number of events is growing, I would like to show you this plot. So on the y-axis and these gray lines indicates the mass of the compact objects, and this is ranked in ascending order. So the blue dots here are the binary compact objects. So these are the two masses, and the arrow indicates the result of the merger. For the first run, so the first catalog we got a couple of years ago. This is here, this one is I hope you can see it there on the big screen. The two dots are the two neutron stars, so the binary neutron star, the first detection of one that I will mention later on again. And these yellow dots represent the detection of neutron stars via electromagnetic detection, so it's basically pulsars. And these red dots are black holes that belongs to X-ray binaries. Now, if we move on to the second catalog that we got, this is, we can see that we start to populate more the different range of masses for the black holes here. And this is the latest one. This is the latest catalog that we have so far. And you can see that we start to cover really a very wide range for the masses of the black hole systems. And also we started to detect, we detected two black hole neutron star systems, and we have more than one now detection of binary neutron stars. So yeah, so far we have about almost 100 events, and yeah, the future is promising, and we expect to have many more in the near future. So I would like to mention two of the, give me a second. Yeah, I would like to mention two of the most interesting cases that we have so far. One is GW-19-0521, which is the most massive event detected today. This is a system of two black holes. So one of 85 solar masses and the other of about 66, that they give, when they merge, they give a result of 142 solar masses black hole. Why is so interesting? Because the primary black hole, so the most massive one, is in what we call the pair instability mass gap. So according to stellar evolution models, very massive star systems leave behind no remnant after the supernova event. So this, based on the stellar evolution models, we shouldn't have black holes form beyond a certain mass. And this is within this pair instability mass gap where we don't expect a black hole. So this, in fact, challenging our stellar evolution models, this system. The second case is GW-17-0817, which is the first binary neutron star detected. And this was also very special because we were able to detect the electromagnetic counterpart of this event. It was amazing because we could cover between radio to X-rays, gamma rays, and we were able to identify a kilonova and short gamma ray burst. Here is from Hubble Space Telescope, and this is the event, and the short gamma ray burst, well, the afterglow, in fact. And yeah, so since we have the electromagnetic counterpart, we were able to identify the host galaxy of this very first binary neutron star system. The host galaxy is NGC 4993. It's an early type galaxy with a stellar mass of about 10 to the 11 solar masses, and most of its star formation rate was taking place about 11 giga-years ago. And more or less at the time that this event was detected, I started working on this field, on gravitational wave events. And there was a lot of tension and discussion about why this is the very first host galaxy detected. If we are having some tension because we were expecting to have as a host galaxy, or the most likely host galaxy, a star-forming galaxy. Instead of that, we had an early type and all galaxy, right? So now I will come back, of course, to this discussion later. So from this, all these catalogs, all these binary compact objects that we have that were detected by LIGO-Virgo-KAGRA collaboration, a lot of interesting and exciting questions appear. For instance, I mentioned this before, but the origin of black holes with masses about 45 solar masses in this penny-stability mass gap. There is also, I didn't mention, but there is a mass gap between the masses of the neutron stars and the black holes. And, but it's from the stellar evolution models, there is not a clear explanation for that. And so since we started to cover all this, also this range, we are wondering if it exists or not, this mass gap between neutron star and black holes. And well, and there are a lot of questions, including also if we started to talk about primordial black holes yesterday, and in the community, there is a lot of debate also if we are detecting multiple formation channels, in particular for the binary black holes, and if we have detected the collapse of primordial black hole binaries in some of these detections that we have now. Okay, now in the future, we in the O4, so the fourth run, will start this year in mid-December, and it is expected to last a total of 13 months. So we will have many more sources in the near future. And yes, and we have the O5, and also there are a lot of plans about what is called the third generation of gravitational wave detectors with the Einstein telescope and Cosmic Explorer that will be the future of gravitational wave event detections. So now, why the host galaxies of merging binary compact objects? Now I will try to tell you why I think it's very interesting and why understanding and exploring the host galaxies can help us to understand a lot of open questions within the gravitational wave astrophysics. So the first one is because they can help us to constrain the stellar evolution pathways. I won't enter into the details of these plots, but just these two papers, one is using universe machine simulations, and the other is using a galaxy sample from the SLOAM. What they use is the galaxy population, and with different constraints for the delay time distribution. The delay time distribution is the time between the formation of the binary compact object, or the binary system, up to the time the binary compact object merge. And I will refer to this delay time afterwards again. So, and there is a lot of debate about how is the shape of this delay time distribution. And of course, depending on the stellar evolution pathways, this delay time distribution changes. So in these two papers, and there are more like this one using electricity NG, these authors try to explore how the properties of the host galaxies changes based on different features or properties or shapes for the delay time distribution. The second reason is because they help us to identify the electromagnetic counterpart of gravitational wave events. What is happening now is that LIGO-Virgo-KAGRA is starting to release or send alerts when they detect a gravitational wave event. But the problem is that the sky localization, when they report this alert, the sky localization is very, very wide. So it's about of hundreds and thousands square degrees. That means that if one team wants to look for the electromagnetic counterpart, need to target and study a very large region on the sky to find this counterpart. But if we know in advance what are the properties of the most likely host galaxies, we will be able to reduce this very area on the sky and just focus on specific places on this area. The third reason is because the gravitational waves are what we call standard sirens. And so if we know the host galaxies, the properties of the host galaxies at which are, we can detect or identify the redshift where this gravitational wave event happened, and combined with all the other properties that we can retrieve from the detection, we can estimate and constrain the Hubble constant. So this will be a new way to, exactly that, to constrain the Hubble constant. There are many other reasons, but I will move on because I would like now to focus on to the works and all the results that we have so far with the people like collaborators. So the methodology. So as you can imagine, we are talking about a very wide range in scales, right? Because we are talking about stellar evolution of the order of parsecs, and we are connecting this evolution of the order of parsec with what is galaxy formation and evolution at large scales. So we are really covering a very wide range of ranges. So what we do is use galaxy formation and evolution from hydrodynamical simulation or empirical models, or also from observation, as I showed you before with the SLOAM, and combine this with stellar evolution models that can come from population synthesis models and body simulations for when we want to investigate dynamically formed systems, and also we can use analytical descriptions. Particular, what I use typically is hydrodynamical cosmological simulations like EAGLE, Illustris, TNG, together with population synthesis models. So in particular, so far I was more focused on this formation channel from isolated binary systems. And now I decided to put some of the main results that we got in this last couple of years. So with this machinery of combining, in my case, the galaxy catalog from simulations with the population synthesis code, we can create a population of, again, binary compact objects, binary neutron star, binary black hole neutron star systems in our simulated galaxies, and investigate different properties of our galaxies and combine and understand what are the most likely places, the most likely host galaxies of our binary compact objects. So, and in this one, what we used was the EAGLE simulation with this population synthesis codes. And what you are seeing here is the merger rate per galaxy, which is the number of compact object mergers per galaxy per unit time, as a function of the stellar mass of the galaxy. So the points here, the dots here represent galaxies. The color code represents the metallicity of the galaxies. And so, and each panel represents different binary compact objects. This is binary neutron stars, binary black holes, and black hole neutron star binaries. And as you can see, in all the cases, so the merger rate per galaxy is higher for the massive galaxies, meaning that massive galaxies are the best place to look for merging binary compact objects, basically because the merger rate per galaxy is higher. And also if you, let's say, and this is very clear for black hole binaries and black hole neutron star systems at fixed stellar mass, there is also a nice trend in metallicity where metal poor galaxies, you can see here, metal poor galaxies have a much higher merger rate per galaxy than metal rich galaxies. We also map this in the context of, as you remember, NGC 4993 is the first host galaxy detected. I will focus only on the right panel. And here, this is the star formation rate of the galaxies as a function of the stellar mass. Now here, the color code represents the merger rate per galaxy. This is for binary neutron stars, and the star here represents the properties, so the stellar mass and the star formation rate of NGC 4993. And as you can see, the properties of this first host galaxy is a place where we have a much high, the highest merger rate per galaxy, indicating again that yeah, it's not really an outlier. It's not really a special case. It's where we expect to have a host galaxy, where, yeah, we expect to have the most likely host galaxies. Now, so all this is in the, all these plots I show you so far were in the local universe. We also extend our analysis to high redshift. And also we split our galaxy catalogs based on the specific star formation rate, so high and low specific star formation rate galaxies. And we study, so this is the merger rate density, is the number of events per unit volume per unit time as a function of redshift for the 3 different binary compact objects we study. And what we found is that, so the red is for low specific star formation rate, that would represent the early type galaxies. And as you can see, at low redshift, the early type galaxies dominate and are the most important galaxies to understand and to explain the merger rate density. While at high redshift, more or less about at redshift 1, this trend reverses, and the galaxies with high specific star formation rate, which would be more or less late type galaxies, dominate the merger rate density. With all this analysis, we provide an astrophysically-motivated criterion for the host galaxies. So we created in a third paper some catalogs to provide what are the properties where it's more likely to detect a binary compact object. In particular, these 2 plots here are for binary neutron star at redshift 0.1 and 6, and this shows you the star formation rate as a function of the stellar mass of the galaxies, and the color code represents the host galaxy probability. Okay, so now this approach that I use using hydrodynamical cosmological simulations with population synthesis codes, since allow us also to understand and investigate the distribution within the galaxies. So, because we can identify, or we can, of course, with the taking into account the resolution that we are able to map in a simulated galaxy, but we can identify the mergers within the galaxy and understand the evolution of them in time within the galaxies. So in this work led by Rosalba Perna, what we did was to use Illustris TNG50 and investigate the host galaxies and the electromagnetic counterparts of binary neutron star mergers from the perspective of our first binary neutron star GW-170817, and see how is the distribution and how the different, in particular in this case, I will show you now, how the kicks because as you can imagine, so we have the binary system that evolves and converting into neutron stars. But during this process, we have supernova events, and in this supernova event can produce a kick. This, of course, for this each star in the binary system, and these kicks can, of course, create displacement or the movement of the binary systems, moving it to the outskirts of the galaxy. I don't know if you are familiar here, but there is within the host galaxies of short gamma ray bursts, so it would be like the electromagnetic counterparts of our binary neutron stars, or some of the cases, there is a very large percentage of about, if I'm not wrong, about 20% of our systems that are hostless. So we cannot identify a host galaxy for these short gamma ray bursts. So with this machinery of combining or identifying binary neutron stars and electromagnetic counterparts, we use Illustrious TNG50. Yeah, since we have the velocity kicks from our supernovas from these binary systems, and we have also the delay time distributions, so combining these two properties, we can identify the position where the system formed and the position where the system merged. And for that, we select 4 beams in stellar masses for our simulated galaxies. So between 10 to the 8 solar masses to 10 to the 11 solar masses. And we picked 4 different redshift. And here what you can see is this is the distribution in space for our 4 beams. The dashed lines represent the distributions where the binary neutron stars are placed, so where they are formed, and the field lines indicate the position where they emerge. And as you can see, there is a very strong displacement, and the shift of these mergers is much higher for in the case of M1. M1 is the lowest mass beam for our simulated galaxies. In this paper, we also as I wrote here about, as you follow this dashed line, 40% of our binary neutron stars from M1, from the galaxy group M1, in the lowest mass beam, is found at distances above 25 kiloparsecs. With this, we also, Rosalba follow and investigate the afterglow of these events. The afterglow is all this emission between radio, optical, X-ray that is produced between the interaction of the jets that are produced by the short gamma ray burst and the interstellar medium. And of course, as you can imagine, if the merger is in the outskirts of the galaxies, we expect to have much lower afterglows that are much more difficult to be detected here on Earth. And well, I just summarize, but because we don't have much time, but the results that she found was that about 30% of binary neutron star mergers are expected to have detectable afterglow radiation when we adopt a randomly oriented jet for our short gamma ray bursts. Okay, so in the last slides, I would like to mention an ongoing work led by Filippo Santoliquido. He's a PhD student in Padova. And now, so the big problem that we have in the approach that I use combining hydrodynamical cosmological simulations of the galaxy catalog from these simulations with the population synthesis codes is that we need a lot of computational time. And this approach, led by Filippo, is much simpler and it's much faster to run. It's based on observational scaling relations between the stellar mass, the star formation rate, and the metallicity of the galaxies. So we create a machinery to map and to evolve the galaxies, so from a high redshift to present, and populate these galaxies based on these scaling relations with binary compact object mergers. And I will just show one of the results here. This is it's a dense plot also. So this FG and AG indicates because we investigate the properties of the galaxies where the binary compact objects form. and the HG is the galaxies where the binary compact objects merge. And we investigate this, as I said, at high redshift. Here it's redshift 4 up to, so at present, redshift 0. And I hope you can see, but the field lines are, so the host galaxies, and the dashed lines are the formation where the binary compact objects form. Each row, so the first row is for binary black holes, the second row is the black hole neutron star binaries, and the last row is for binary neutron star systems. And each column represents is a different run for our stellar evolution models. So it's this alpha 1, alpha 3, and alpha 5. As you can see, it's connected with a phase that is called the common envelope, that is very challenging for the stellar evolution models and can modify a lot the delay time distribution of our binary compact objects. But yeah, just to summarize, just briefly, one of the main results of this plot is that, as you can see, for, and this is much more clear when we have alpha 5, that so the binary compact objects is much more bound, and that and this is the stellar mass, I said, the stellar mass of the binary of the host galaxies is much higher for the host galaxies where they merge than when they form. So what basically is telling us that these binary black holes, for instance, have a very long delay time. Instead, for binary neutron stars, you see that this alpha 5 parameter does not affect much, and so you can see the distribution of the dashed lines and the field lines are similar, indicating us that the stellar mass properties of the galaxies where they form and merge are more or less quite similar or the same. Well, there are many more results. This is very preliminary, and yeah, and we expect to have a forthcoming paper very soon. So as a take-home message, I would like to, I hope I convince you that, yeah, the massive galaxies are the most likely to host a binary compact object merger. We found that in the local universe, the merger rate density is dominated by the merging binary compact objects in galaxies with a low specific star formation rate, which means that our first host galaxy, GC 4993, is not a very special case, but is where we expect to have a binary neutron star detected. That about, and then, yeah, about 30% of binary neutron star mergers are expected to have a detectable afterglow radiation. And yeah, well, now we have a new machinery to investigate the host galaxies based on these scaling relations with this paper from Filippo. And yeah, I think that our contribution will be very important, and in particular to understand and to provide hints for the future electromagnetic counterpart detections. And this will be also very important in the near future with the Vera Rubin Observatory that, yeah, of course, will provide a lot of transient events. And yeah, that's all. Yeah, I can mention if you have more questions related with the what I mentioned during the talk, I'm happy to take questions now. Thanks.
Thank you very much, Celeste. So we have time for questions, maybe from the audience or there. Nelson?
Hi, Celeste.
Hi.
Thank you for the talk. It's actually quite interesting. So I was wondering, I mean, when you showed the merger rate as a function of stellar mass, it's sort of,
This one.
yeah, I mean, there's the increase is basically, I mean, the increase in the merger rate is of the same order of magnitude as the increase in stellar mass. So it's actually, I mean, the rate per, I guess, per solar mass is basically constant.
Yes,
And,
exactly.
and smaller galaxies are actually more abundant. So shouldn't we have expected to detect the first counterpart in a small galaxy because of this?
Yeah, it's a good point, but yeah, this is something we discussed a lot in the past. Yeah, the fact that yeah, we have many more events in the massive galaxies. Yeah, that's why we expect. Do you understand? That's why we expect that they are more the most likely. But yeah, I understand your point. This was a lot of debate on that. Yeah, but yeah, the fact that again we have much more stellar mass because at the end is that is a tracer of the stellar mass. That's the main property
We're back.
here.
Celeste, sorry,
Yeah.
we had a little problem with internet. Can you repeat your last 20 seconds?
Okay. No, I said that yes, is we expect to have much more stellar mass, of course, the massive galaxies, and we have more events. That's the reason we claim that we expect that. And yeah, that's what we think.
Okay.
I see your points that are more the low mass galaxies, but of course we have less mass and we have less events there. It's just a matter of that.
Possibly when looking for the counterparts, the brightest targets are the ones that people look at.
Yeah.
That's easier to see, to look at a few bright galaxies rather than others.
Yeah. Let me say something I forgot to mention before, but there is also, so in the massive galaxies also, of course, they are older, so they collect a lot of stars there that with different, so we have binary compact objects with different delay time distributions, right? That's something also very important because it's not happening in the low mass galaxies, right? So we have a much interesting also population in that case in the massive ones because because of that, no, we have much more time to produce star formation and also eventually merge. And and also the fact that about observational data claims that I think it's about 70% of the stellar mass in presence is in early type galaxies. That's why also we expect that early type galaxies are the most dominant in the local universe, or where we expect to have merging binary compact objects.
Vladimir and Cynthia.
Hi, Celeste. To calculate the merger rates, you need the stellar population synthesis for binary formation and evolution. So
Yes.
what is the most uncertain phase in these synthesis models? What is the key, let's say, parameter?
There are so many.
You need to calculate.
Yeah, there are. I have to say that there is I don't know if I have it at the end or I didn't put it. But the population synthesis codes are a full topic alone, you know. And there is people just focus on the improving and having the best population synthesis codes that reproduce our binary compact object mergers, right? And yeah, there are lots of parameters or uncertainties, like in the case of our hydrodynamical cosmological simulations, right? And but in particular, one of the main aspects, I think, is this common envelope that I mentioned, because first is, as far as I know, it's something that was not detected itself. So it's a stage, right, where the mass transfer between the secondary and the primary, so to the primary, is unstable, create this envelope of hydrogen between this binary system. And how bound is this envelope is not very clear. And that's in fact why I show you this here, this alpha 1, alpha 3, alpha 5 is this parameter connected with the how bound is this envelope to this in this binary system. This is one of the main uncertainties. And in fact, for instance, there are different stages, because what we need to do basically in the binary compact system is to shrink the orbit of the system up to finally they merge within a Hubble time. And yeah, there are other new papers, one from well, using another population synthesis code is Cosmo, if I'm not wrong, and Van den Son, I think is the first author, where they find that not only this stage, so the common envelope, allow the binary compact object to shrink and merge within Hubble time, but also the mass transfer between the binary systems can also produce yeah, at some point some dynamically changes that shrink the orbits of the binary systems. So yeah, I would say that the common envelope is one of the main things, and again, connected with that, how the binary compact object shrinks to merge within a Hubble time, and what are the processes behind. And something that I decided to, I know I'm run out of time, but something that I decided not to mention much here, but I would like to tell you all, is that there are different formation channels for these binary compact objects. So we focus mainly on isolated systems or I focus on my talk, but there are other systems that, or there are other formation channels that are, when we have binary compact objects that are dynamically formed in star clusters or globular clusters. And yeah, this will also provide us features or different features. And of course, in the population synthesis code are not included. Well, was very long reply, sorry.
Hi, Maria Celeste. Yes, my question had to do also with what Vladimir asked, so I'm going to change my question. I was also curious about, you showed us that at redshift 0, the probability was higher, like in elliptical galaxy, let's say, but it changed at higher redshift, right?
Yes.
So, yes, that. So my question is, what is driving this change in the change of probability?
Yeah, this is in fact also connected with these delay time distributions, right? What is happening is that, well, first, the stellar mass is the main driver, we said, but so at the low redshift, what we are having is a very wide range of binary compact objects with different delay times here. And they are located or placed in early type galaxies. Instead, in the late type galaxies, so we are forming stars now, and the only ones that are merging at low redshifts are those binary compact objects with short delay times, right? So that form and merge in very short period of time. Since at high redshifts, we are not giving them time to evolve and merge. And so, and that's why in late type galaxies, we have many more, so stars forming and are the main drivers of our merger rate density. Because, yeah, we have many more stars and many more events, many more mergers producing in these galaxies. I hope it's clear. There are more plots. I really know I'm running out of time, but yeah, if you go to my paper, I have a very long explanation of that. These are the delay times of the early and late type galaxies.
Okay, so we will move to our next speaker. Let's thank Celeste again.
Thanks. And if you have questions, I'm on the chat on Discord. Yeah. Let me see how to stop. Yeah, here.